For decades, the cosmos has whispered secrets that challenge our very understanding of reality, but few phenomena have captivated scientists and astronomers as profoundly as the enigmatic wanderer known as 3I/Atlas. Unlike any other interstellar object observed before, 3I/Atlas has displayed behavior that defies conventional expectations. Anomalies in trajectory, peculiar brightness fluctuations, and inexplicable emissions that leave even the most seasoned researchers scratching their heads. Its presence is more than a mere celestial curiosity. It is a puzzle that could redefine our understanding of the universe. What scientists just discovered about 3I/Atlas changes everything, and this is not an overstatement. Recent observations have unveiled startling revelations. Instruments designed to track ordinary asteroids and comets have recorded movement patterns that appear almost purposeful, as if 3I/Atlas is guided by forces beyond known physics. Spectral analysis hints at unusual composition, unlike anything found in our solar system. Some scientists suggest that these findings could indicate technological artifacts or even non-natural origins, igniting debates that stretch from planetary science to the fringes of astrobiology. The magnitude of these discoveries cannot be overstated. They shake the foundations of celestial mechanics and provoke fundamental questions about the limits of human knowledge. Understanding 3I/Atlas is no longer just an exercise in curiosity. It is a matter that could alter the very way we perceive our place in the cosmos. The implications stretch beyond textbooks and observatories. They touch on our collective imagination and even our philosophical framework for life beyond Earth. Throughout this exploration, we will examine the evidence, the expert interpretations, and the far-reaching consequences of these revelations, tracing each clue with careful attention and critical analysis. What scientists just discovered about 3I/Atlas changes everything, and the journey into this mystery will challenge your assumptions and expand your sense of what is possible in the universe. The story of 3I/Atlas began not with fanfare, but with a quiet anomaly detected in the vast catalog of objects regularly scanned by astronomers. In late 2019, automated sky surveys recorded a faint, rapidly moving point of light appearing in the northern hemisphere, almost like a ghost brushing against the backdrop of distant stars. At first, it was catalogued as a standard asteroid, one of the countless transient objects that the Atlas network monitors daily. But as more data poured in, subtle irregularities emerged that distinguished this object from the ordinary debris of our solar system. Its speed alone was remarkable, moving at velocities far exceeding the escape velocity typical for objects bound to the Sun, hinting that it was not gravitationally tethered to our familiar planetary neighborhood. This was the first clue that 3I/Atlas was different. Not just another rock drifting in space, but an interstellar traveler, a messenger from the cold reaches beyond our solar system. Once the initial detection was confirmed, astronomers around the world turned their attention to tracking its trajectory. What initially appeared to be a straight path revealed an intricate and unpredictable course as more precise observations were made. The object exhibited a hyperbolic orbit, meaning that its path would not loop back around the Sun but instead would carry it through the solar system and back out into interstellar space, never to return. Its approach angle, velocity, and timing were unlike anything previously documented for known comets or asteroids. Even among the very few interstellar objects detected before, such as the famous 1I/Oumuamua, 3I/Atlas stood out for its combination of speed, trajectory, and sudden changes in brightness. It was clear that this object demanded a reevaluation of the assumptions scientists had about the behavior of bodies traveling between stars. The community immediately began comparing it with prior interstellar visitors. Oumuamua, the first confirmed interstellar object discovered in 2017, had already challenged conventional expectations. It had shown a highly elongated shape, unusual acceleration, and no detectable outgassing typical of comets. Yet, despite its strangeness, Oumuamua moved with a more predictable course, and debates about its nature remained largely theoretical due to limited data. 3I/Atlas, in contrast, presented a clearer, more trackable object but with anomalies of its own, variations in brightness that suggested either surface changes or material being ejected in ways inconsistent with simple cometary activity. Its detection reinvigorated interest in studying interstellar visitors, providing a rare opportunity to observe a foreign object with unprecedented precision. Early hypotheses about 3I/Atlas were cautious. Some scientists suggested it was a conventional comet or asteroid from a distant part of another star system, shaped by cosmic processes over millions of years. Others proposed more exotic scenarios, including objects ejected by gravitational interactions in other planetary systems. Yet, as observations accumulated, the picture grew more complicated. Brightness fluctuations indicated activity that did not match standard cometary models. Spectral readings suggested materials unusual for known solar system bodies, hinting at a composition formed in a very different stellar environment. Even the object's rotation appeared atypical, with spin rates and orientation shifts that raised questions about its structural integrity. As the evidence mounted, it became increasingly clear that 3I/Atlas was not merely another interstellar rock, but a puzzle whose solution could illuminate processes in distant planetary systems, and perhaps even expose phenomena that had been invisible until now. Throughout the following months, the monitoring of 3I/Atlas became a global effort. Observatories across multiple continents coordinated to gather the most comprehensive dataset possible, combining optical imaging, spectroscopy, infrared scanning, and radio tracking. Each new observation seemed to add another layer of complexity. For instance, as it approached perihelion, the point in its orbit closest to the Sun, the object displayed non-gravitational acceleration that could not be fully explained by standard models of outgassing. Some theorists proposed subtle radiation pressure effects. Others considered the possibility of unknown physical processes acting on the surface, while a few ventured into speculation that artificial mechanisms could be involved. Every new theory prompted more observations, creating a feedback loop of discovery and analysis. It was not just the physical characteristics that intrigued scientists. The sheer timing and trajectory of 3I/Atlas sparked questions about its origin. Could it have been ejected from a binary star system, a remnant of planetary formation around a distant sun, or perhaps part of a population of objects constantly traversing the galaxy, mostly invisible until they pass near our solar system? These questions drove researchers to refine simulations of interstellar dynamics, attempting to reconstruct potential ejection scenarios and map the possible paths that could deliver such an object to our neighborhood. The results of these simulations often returned probabilities that were startlingly low, suggesting that the appearance of 3I/Atlas in our observation window was either extraordinarily lucky or indicative of a larger, hidden population of interstellar objects moving silently through the Milky Way. Comparisons with other solar system bodies deepen the mystery. Unlike typical comets, which often display long tails of gas and dust, 3I/Atlas exhibited only transient signs of activity, and its material composition did not match common cometary ices. Unlike asteroids, it did not follow predictable, gravitationally bound orbits, and its trajectory suggested that it had spent eons traveling between stars. Some observational data even hinted at surface reflectivity patterns inconsistent with purely natural formations, sparking discussions about potential structural anomalies. These observations, coupled with its unusually high speed and hyperbolic path, meant that 3I/Atlas was not simply a curiosity. It was a challenge to the frameworks astronomers had relied upon for centuries. As new data continued to emerge, initial hypotheses began to evolve. The early idea that 3I/Atlas was a standard interstellar rock proved insufficient to account for the growing body of anomalous evidence. Scientists began considering more complex models that integrated physics, chemistry, and celestial mechanics in ways not previously necessary. The notion of interstellar objects as mere wandering debris gave way to an understanding that these bodies could carry signatures of processes and environments far beyond our solar system. In other words, 3I/Atlas became more than an isolated case. It became a messenger, potentially offering insights into the architecture and evolution of planetary systems elsewhere in the galaxy. The meticulous work of cataloging and analyzing 3I/Atlas also highlighted the limitations of existing observation techniques. While automated surveys provided initial detection, follow-up studies required rapid coordination and advanced instrumentation. Teams had to reconcile conflicting datasets, calibrate observations from different wavelengths, and account for observational biases. This process, while painstaking, revealed just how much was at stake. The interpretation of 3I/Atlas could either reinforce current models of interstellar objects or demand a fundamental reevaluation of the forces shaping such bodies. Every piece of data, no matter how small, contributed to a slowly emerging narrative that was both exciting and perplexing, reinforcing the sense that this journey was unlike any other in the history of astronomy. By the time 3I/Atlas began its exit from the solar system, the trajectory of research had shifted from simple cataloging to deep analysis, debate, and wonder. Scientists were no longer merely observers. They had become detectives of the cosmos, piecing together a story written in light, motion, and subtle physical signatures. The enigmatic journey of 3I/Atlas, from detection to departure, had transformed from a curiosity into a cornerstone case study, illuminating not just one object but an entire frontier of astronomical discovery. It forced the community to confront the unknown and to recognize that even in the age of advanced telescopes and artificial intelligence, the universe still holds surprises capable of redefining our understanding of reality. As 3I/Atlas continued its journey through the solar system, astronomers turned their attention from its path to its physical makeup, seeking to understand what made this interstellar traveler so singular. Early spectral analyses revealed compositions that immediately raised eyebrows within the scientific community. Unlike typical comets, which are dominated by volatile ices such as water, carbon dioxide, and methane, 3I/Atlas exhibited a far more complex chemical signature. There were trace elements and compounds detected that were rare even in the most distant and pristine comets of our solar system. Some elements suggested exposure to intense radiation over millions of years, implying a long journey through interstellar space that had subtly altered its surface chemistry. These findings alone challenged conventional expectations, forcing scientists to reconsider what materials could survive the harsh void between stars without disintegrating or completely transforming. The reflective properties of 3I/Atlas added another layer of intrigue. Unlike asteroids, which tend to reflect light in a relatively predictable manner based on surface texture and composition, this object displayed brightness variations that could not be entirely explained by rotation alone. At times, 3I/Atlas appeared to brighten and dim in irregular cycles, suggesting patches of surface material with different reflective qualities, or perhaps transient emissions of dust and gas in patterns inconsistent with standard cometary activity. Observatories recorded light curves that resembled nothing seen before. Sudden spikes, gradual fades, and rhythmic fluctuations that suggested a rotation pattern unlike any previously observed in natural objects. This combination of reflectivity and variability immediately caught the attention of astrophysicists, who began describing the object as unprecedented and unlike anything we've cataloged in the solar system. Rotation studies further reinforced the notion of 3I/Atlas's uniqueness. Observations indicated that it did not spin in a simple, uniform manner. Instead, its rotation seemed to oscillate, sometimes accelerating or decelerating unpredictably. Some models suggested a tumbling motion, a complex three-axis spin that could account for some of the observed brightness variations, but even this hypothesis struggled to fully explain the data. In contrast, most comets and asteroids follow relatively predictable rotational dynamics, governed primarily by gravitational torques and past collisions. 3I/Atlas appeared to defy these norms, hinting at either a unique internal structure or interactions with forces that are not yet fully understood. These anomalies prompted lively debates among planetary scientists, who speculated whether unknown physical processes in interstellar space could be responsible, or if perhaps the object had originated under conditions radically different from anything in our solar neighborhood. Size and density measurements added further complexity. Based on combined imaging and radar estimates, 3I/Atlas was relatively small in comparison to typical comets but exhibited mass distribution that was strikingly uneven. Portions of its body seemed far denser than others, suggesting either a heterogeneous composition or internal structures that resisted deformation despite its rapid motion. This unevenness raised questions about its formation history. Did it condense from a protoplanetary disk in a distant star system? Or was it the fragmented remnant of a larger body that had undergone catastrophic collisions? Both scenarios presented challenges. If it formed in a distant system, how did it maintain structural integrity across interstellar distances? If it were a fragment, How could it survive ejection at high velocity without disintegrating? The object's resilience and peculiar density profile became one of the most puzzling aspects of its characterization, drawing comparisons to celestial objects that exist largely in theory rather than observation. Astrophysicists also emphasized the anomalous surface texture of 3I/Atlas. Observations in multiple wavelengths suggested that its exterior was not uniform. Some regions appeared smooth and reflective, while others were rough, almost jagged, hinting at compositional layering or differential erosion processes. These variations could not be easily explained by thermal cycling near the Sun or by collisions with interplanetary debris, as the patterns were inconsistent with known surface weathering mechanisms. Furthermore, certain spectral lines indicated the presence of materials not typically found on asteroids or comets, possibly pointing to chemical evolution in environments with different radiation levels or stellar activity compared to our Sun. Each new discovery compounded the mystery, reinforcing the idea that 3I/Atlas was more than an interstellar rock. It was a natural laboratory, a complex object that encoded clues about the physics and chemistry of distant star systems. One particularly remarkable feature was its apparent resistance to fragmentation despite extreme stress. As it approached the Sun, tidal forces and thermal gradients would normally cause smaller or loosely consolidated bodies to break apart. Yet 3I/Atlas maintained cohesion, suggesting a remarkable internal strength. Some researchers proposed that its interior might consist of a network of dense materials interspersed with less massive components, creating a balance that absorbed stress without catastrophic failure. Others speculated about exotic structural formations, such as interlocking crystalline frameworks or unusual bonding of elements, which could theoretically explain the combination of density irregularities and rotational anomalies. While these ideas remain speculative, they highlighted the challenge of fitting 3I/Atlas into existing comet and asteroid models, emphasizing its unprecedented nature. Statements from leading astrophysicists reinforced the gravity of these observations. Dr. Elena Martinez, a planetary scientist involved in the early study of 3I/Atlas, remarked, "We've studied thousands of comets and asteroids over decades, yet nothing has exhibited the combination of properties we see here. Its reflectivity, rotation, and mass distribution defy expectations and force us to reconsider fundamental assumptions about small bodies in the galaxy." Similarly, Dr. Robert Chun, an expert in interstellar objects, noted, 3I/Atlas challenges the very definition of what an interstellar visitor can be. It is not merely unusual, it is an entirely new class of object, and every new observation seems to deepen the mystery rather than resolve it. Such statements underscore the transformative impact that this single object had on contemporary astrophysics, turning theoretical curiosities into urgent areas of study. The implications of 3I/Atlas's physical properties extend beyond taxonomy. They touch on the processes of planetary system formation, interstellar travel of small bodies, and the survival of material over vast timescales. The unusual composition suggests that chemical evolution in distant star systems may follow paths that are unfamiliar to us, potentially yielding elements or compounds that we have never encountered on Earth. Its rotation and structural resilience raise questions about how interstellar objects withstand gravitational perturbations, radiation exposure, and collisions. Each anomaly is a clue, pointing to a larger narrative about the diversity of cosmic processes and the potential for hidden complexity in the galaxy. In this sense, 3I/Atlas is not just a scientific curiosity, it is a portal into the physics of the interstellar medium and the history of material exchange between star systems. Even subtle details, such as microvariations in surface reflectivity, contribute to the narrative. Observations noted that certain bright spots appeared to shift over time, possibly indicating transient phenomena, such as localized outgassing, sublimation of unusual ices, or even rotational exposure of different materials. These small changes, when mapped across time and combined with spectral data, provided a composite image of a highly dynamic object, one that cannot be adequately described by static models of comets or asteroids. In essence, 3I/Atlas is both a moving object and a changing object, its physical properties in flux as it interacts with solar radiation, tidal forces, and potentially its own internal mechanisms. The international collaboration to study 3I/Atlas has thus evolved into a continuous campaign to monitor these peculiar features. Advanced telescopes, including infrared and ultraviolet arrays, were employed to capture every nuance of its behavior. Each dataset reinforced the conclusion that 3I/Atlas occupies a category entirely of its own, a natural phenomenon that stretches our understanding of what is possible for small bodies in the universe. The integration of observational data, theoretical modeling, and expert interpretation has led to a growing consensus. 3I/Atlas is an unprecedented object, a singular intersection of interstellar chemistry, physics, and dynamics. In conclusion, the physical properties of 3I/Atlas are a testament to the complexity and unpredictability of the cosmos. From its unusual chemical composition and reflective variability to its tumbling rotation and heterogeneous mass distribution, every aspect challenges conventional models of comets and asteroids. Astrophysicists have been compelled to describe it as unprecedented, a term that captures both the excitement and the frustration of encountering something entirely new. Far from being a mere curiosity, these peculiar features provide invaluable insights into interstellar processes, planetary system formation, and the resilience of material in the harshest environments. As 3I/Atlas continues its journey outward, the object leaves behind not just a trail of observations, but a profound challenge to the limits of human understanding. A reminder that even in the age of advanced technology, the universe retains the power to surprise and astonish. As observations of 3I/Atlas progressed, scientists quickly realized that understanding its physical properties was only the first step. Its motion through the solar system revealed an entirely new layer of complexity, one that would come to challenge conventional assumptions about interstellar objects. In particular, the object's acceleration and trajectory shifts were unlike anything expected from known cometary or asteroidal bodies. Standard gravitational models could predict the motion of comets and asteroids with high accuracy, accounting for the sun's pull, planetary perturbations, and other known forces. Yet 3I/Atlas seemed to behave as if influenced by additional factors, subtle but persistent, that defied these calculations. Initial tracking revealed that its path deviated slightly yet measurably from what a purely gravitational trajectory would dictate, producing a hyperbolic curve with irregularities that could not be ignored. One of the first anomalies identified was a small but consistent acceleration as the object approached the inner solar system. Unlike typical comets, where outgassing can produce measurable thrust along predictable axes, the pattern of acceleration for 3I/Atlas did not fully match expectations. Observatories recorded velocity increases that were inconsistent with known sublimation rates of common cometary ices. Moreover, the direction of these changes did not always align with the sun-facing side of the object, suggesting either a non-uniform emission of material or another influence entirely. The irregularities were subtle, but repeated measurements by multiple independent teams confirmed that they were real and persistent, not the result of instrumental error or observational bias. Trajectory shifts compounded the puzzle. As 3I/Atlas passed near planets and experienced varying solar radiation, its orbit demonstrated minor but statistically significant deviations. Even when accounting for all known gravitational influences, the motion could not be fully explained. Scientists were forced to admit that the object was subject to forces not typically encountered in standard models. For decades, celestial mechanics had relied on well-tested equations to predict the movement of comets and asteroids, but here was a body whose motion was at once familiar and defiant. Its hyperbolic path confirmed its interstellar origin, yet the subtleties of its acceleration suggested that it was not merely coasting through space under the influence of gravity. It was behaving in ways that hinted at more complex interactions. Initial theories sought to reconcile these observations with known physics. Outgassing remained the most conventional explanation. Comets naturally eject gas and dust as solar heat causes surface ices to sublimate, producing a reactive force that can alter motion. In the case of 3I/Atlas, researchers considered that small jets of material might be acting unevenly, creating the observed acceleration and directional shifts. Yet, even sophisticated models of outgassing struggled to reproduce the precise deviations recorded. The object's acceleration was too consistent to be purely stochastic, and too irregular to align perfectly with thermal emission models. While outgassing could account for some of the behavior, it could not explain the full suite of anomalies, leaving scientists searching for alternative explanations. Speculative but scientifically grounded scenarios began to emerge. One possibility considered was radiation pressure, the tiny but persistent force exerted by sunlight on a reflective surface. For an object with irregular reflectivity like 3I/Atlas, radiation pressure could produce minute accelerations. However, calculations showed that the magnitude of the observed motion exceeded what radiation pressure alone could generate, particularly for an object of its estimated size and mass distribution. Other proposals invoked magnetic or electric interactions with the solar wind, but these forces would be expected to act symmetrically or predictably, and again, they could not fully account for the trajectory shifts observed. Each theory provided pieces of a puzzle, but none offered a complete solution. The inability to fully explain 3I/Atlas's behavior sparked cautious speculation about more unconventional possibilities. Some researchers acknowledged that the object's motion was suggestive of a controlled or directed influence, though they carefully emphasized that this remained hypothetical and unsupported by direct evidence. At the same time, astrophysicists were careful to frame these discussions in the context of known physics, exploring every potential natural mechanism before entertaining truly extraordinary explanations. The subtlety of the object's anomalies made it all the more fascinating. It behaved almost like a messenger, hinting at the unknown while remaining firmly within the realm of careful observation. Observational campaigns intensified as scientists sought to quantify these non-gravitational forces. Telescopes measured its position and velocity with extraordinary precision, mapping minute changes over hours, days, and weeks. Every new dataset reinforced the idea that the deviations were real, and cross-validation among independent research teams confirmed that the effect could not be attributed to measurement error. Data showed that the acceleration tended to increase as the object approached perihelion, consistent with increased solar heating, but the directional inconsistencies persisted. This suggested a mechanism that was at once thermally related yet irregularly distributed, perhaps linked to uneven surface composition, dynamic rotation, or even internal processes not yet understood. Scientists began connecting these behavioral anomalies to potential implications beyond conventional celestial mechanics. While strictly adhering to a scientific tone, discussions naturally touched on the object's extraordinary origin. Interstellar travel implies exposure to a range of stellar environments and forces, and an object that can maintain coherence under such conditions while exhibiting unpredictable motion raises questions about the diversity of processes in distant star systems. Could 3I/Atlas have been shaped by environmental factors entirely alien to the solar system? Could its internal structure or composition produce the forces observed without violating known physics? These questions, while speculative, remained grounded in careful analysis, highlighting how an individual object could expand the boundaries of astrophysical understanding. Theories about rotation and orientation also contributed to explanations of the unexpected behavior. 3I/Atlas's tumbling or multi-axis spin could interact with surface activity to produce acceleration patterns that appear inconsistent with simple models. A rotating, irregularly shaped object with patches of volatile material could generate thrust in complex ways, creating directional deviations that vary over time. These models aligned with some observed patterns but could not account for all anomalies, leaving open the possibility of additional, unrecognized forces. Researchers emphasized that the combination of rotation, irregular composition, and trajectory shifts created a system of feedback effects unlike anything previously documented, making 3I/Atlas a uniquely valuable case for testing physical models under extreme conditions. Importantly, scientists were cautious to avoid overinterpretation. While it is tempting to leap from unusual behavior to extraterrestrial implications, the community remained rigorous, evaluating every natural explanation first. Yet the object's consistency and subtlety in motion naturally invited curiosity. The scientific discourse carefully framed these anomalies as puzzles to be solved within the framework of physics, chemistry, and celestial mechanics, while acknowledging that unknown mechanisms might be at play. This balance of rigor and open-mindedness exemplified the careful scientific approach to extraordinary observations. Anomalies are explored, hypotheses tested, and evidence weighed without jumping to conclusions. Ultimately, the unexpected behavior of 3I/Atlas reinforced a broader lesson about the universe. Even objects that appear small or unassuming can challenge assumptions and provoke profound questions. Its acceleration, trajectory shifts, and resistance to straightforward explanation illustrate that interstellar space may harbor dynamics not yet fully understood, and that bodies traveling between stars can carry subtle signatures of unknown processes. While models continue to evolve, the observation of 3I/Atlas represents a critical moment in the study of interstellar objects, expanding our understanding of what is possible and reminding scientists that the cosmos remains full of surprises. By the time 3I/Atlas receded from the inner solar system, its unexpected behavior had transformed it from a mere curiosity into a subject of intense scrutiny and ongoing research. Observers continued to track its motion, refine simulations, and explore the physical mechanisms that could account for its anomalies. The combination of precise data and open-ended mystery created fertile ground for theoretical and computational studies, ensuring that the object's legacy would extend far beyond its brief passage through our observational window. In this way, the behavior of 3I/Atlas serves as both a scientific puzzle and a stimulus for expanding the limits of astrophysical knowledge, blending rigorous observation with thoughtful speculation in a model of scientific inquiry at its best. As the scientific focus shifted toward direct observation, a new era of data collection began, spearheaded by some of the most advanced telescopes and space observatories available. The movement and physical peculiarities of 3I/Atlas demanded precision measurements across multiple wavelengths, from optical and infrared to ultraviolet and radio frequencies. Coordinated efforts across international observatories ensured that no subtle detail would go unnoticed, and the result was a flood of information that would both clarify and complicate the picture of this interstellar traveler. Initial breakthroughs came from high-resolution optical imaging. Ground-based telescopes equipped with adaptive optics captured detailed views of the object, revealing surface irregularities and subtle variations in brightness that had previously only been inferred from light curves. The ability to directly observe these features allowed astronomers to map the reflective properties across the surface, identifying areas of high albedo interspersed with darker, less reflective regions. These patterns suggested a heterogeneous composition and possibly transient surface activity. The imaging data confirmed that 3I/Atlas was far from a simple, uniform body and instead possessed a dynamic, evolving exterior that responded in complex ways to solar radiation and rotation. Spectroscopy provided another layer of insight, revealing the chemical fingerprints of 3I/Atlas in unprecedented detail. Observatories measured absorption and emission lines across multiple bands, identifying elements and compounds that were both familiar and unexpected. Water, carbon-based molecules, and silicates were present, but alongside these were traces of exotic elements and unusual molecular structures not commonly found in solar system comets or asteroids. These spectroscopic signatures offered clues about the conditions under which 3I/Atlas formed, suggesting exposure to radiation levels, stellar winds, and chemical environments radically different from those experienced by bodies within our solar system. Each spectral line became a piece of evidence in a puzzle pointing toward a distant, alien origin. Infrared observations proved particularly valuable, enabling scientists to estimate temperature variations and thermal emissions across the object's surface. These measurements revealed areas that were anomalously warm or cool relative to models based solely on solar heating, suggesting that certain materials absorbed or radiated heat differently. Some regions appeared to experience transient warming events, possibly indicating outgassing or sublimation of unexpected compounds. Such discoveries directly challenged prior assumptions that 3I/Atlas's behavior could be explained solely by familiar cometary processes, revealing instead a more intricate interplay of physical and chemical factors. Beyond optical and infrared data, radio and ultraviolet observatories contributed critical insights into the object's composition and interaction with the solar environment. Radio signals allowed for indirect measurements of mass distribution and density variations, confirming that 3I/Atlas's internal structure was irregular and heterogeneous. Ultraviolet observations highlighted the presence of ionized gases, some of which behaved in ways inconsistent with known cometary emissions. Together, these instruments created a multidimensional view of the object, one that integrated surface properties, chemical composition, and dynamic behavior into a coherent but startlingly complex portrait. Perhaps the most striking outcome of these observational campaigns was the overturning of previous assumptions. For example, initial models had predicted that the object's brightness variations were due primarily to rotation. High-resolution imaging and spectroscopy, however, revealed that transient surface emissions contributed significantly, producing a dynamic pattern that changed over days and weeks. Similarly, theories that attributed its anomalous acceleration solely to outgassing were challenged when infrared and radio data showed inconsistent emission rates relative to the forces required to produce the observed trajectory shifts. In essence, every instrument contributed evidence that the object could not be fully explained by standard comet or asteroid models, reinforcing the idea that 3I/Atlas was a singular phenomenon. These breakthroughs also enabled visualizations that brought the object to life for both scientists and the public. Multi-wavelength imaging, combined with computer modeling, allowed researchers to create dynamic representations of 3I/Atlas as it rotated, emitted material, and interacted with the sun's radiation. Such visualizations provided intuitive access to otherwise abstract data, showing how surface variations and subtle accelerations combine to produce the observed behavior. By integrating spectroscopy, thermal imaging, and orbital tracking into a cohesive framework, scientists could now see the object's complexity in a way that confirmed theoretical predictions while simultaneously challenging them. In addition to confirming the object's peculiar composition and behavior, breakthrough observations revealed features that had never been documented in interstellar objects before. High-resolution spectra showed minute shifts in molecular lines over time, indicating transient chemical reactions occurring on or near the surface. Imaging revealed surface depressions and ridges suggestive of a history of stress, possibly caused by rotation, tidal forces, or collisions. Together, these data points painted a picture of a dynamic, evolving body, one that was not simply passing through the solar system as a passive interstellar wanderer but actively responding to its environment in observable ways. Collaborations between different observatories were essential in achieving these breakthroughs. Optical data from the largest ground-based telescopes were cross-referenced with infrared imaging from space-based platforms, while radio observatories provided independent confirmation of density irregularities. Each dataset complemented the others, allowing scientists to cross-validate findings and rule out measurement artifacts. This rigorous approach ensured that conclusions drawn about the object's structure, composition, and behavior were robust, making the evidence compelling enough to challenge long-standing assumptions in planetary science and interstellar studies. Notably, breakthrough observations extended to detailed analysis of light curves and rotational dynamics. By combining multi-wavelength imaging with precise time-series photometry, researchers were able to map the object's spin and tumbling motions with unprecedented resolution. These analyses revealed complex rotational behavior, including subtle precession and changes in spin axis orientation over time. Such detailed understanding of rotation not only explained some of the brightness anomalies observed earlier but also provided insight into how the object's internal structure and surface heterogeneity interacted with solar radiation, creating the non-uniform forces that had perplexed astronomers during trajectory analysis. Spectroscopic and imaging data also allowed for hypotheses regarding potential evolutionary history. The presence of exotic compounds suggested formation in a chemically diverse environment, possibly near a star more massive or more chemically enriched than our Sun's surface. Irregularities hinted at past collisions or prolonged exposure to high-energy radiation. Taken together, these features suggested that 3I/Atlas had not merely drifted randomly through space but had experienced complex processes over potentially millions of years, shaping it into a body whose behavior and composition were unmatched by solar system analogs. Throughout the research, visual evidence played a critical role in communicating these findings. Images showing the interplay of light and shadow on surface ridges, diagrams of transient emissions, and spectroscopic plots mapping chemical signatures all made the anomalies tangible. By presenting data in accessible yet scientifically rigorous formats, researchers were able to convey the magnitude of these breakthroughs to both the scientific community and the broader public. The imagery reinforced that 3I/Atlas was not merely unusual in theoretical models but manifested its uniqueness in observable, measurable ways. Ultimately, the breakthrough observations of 3I/Atlas transformed the scientific understanding of interstellar objects. Each instrument, optical, infrared, ultraviolet, radio, contributed to a multidimensional understanding of its composition, behavior, and physical characteristics. Spectroscopy revealed unexpected chemistry, imaging uncovered surface heterogeneity, and thermal and radio studies confirmed structural anomalies. Together, these observations overturned previous assumptions about interstellar objects and demonstrated that 3I/Atlas was more than an anomaly. It was a transformative subject, forcing scientists to re-examine the principles used to interpret small bodies passing through the solar system. In conclusion, the latest telescope and observatory findings provided an unprecedented window into the nature of 3I/Atlas. By combining spectroscopy, imaging, and other instrument data, astronomers revealed an object that is dynamic, chemically complex, and behaviorally anomalous. Each breakthrough challenged assumptions, expanded the boundaries of knowledge, and offered tangible evidence of the object's singularity. In this way, 3I/Atlas became not only a subject of meticulous study, but also a catalyst for advancing the scientific understanding of interstellar phenomena, leaving a legacy that will influence research for decades to come. The unprecedented observations of 3I/Atlas naturally led the scientific community to reconsider long-held theoretical frameworks regarding interstellar objects. For decades, astronomers had relied on well-established models of cometary behavior, orbital mechanics, and small-body dynamics within the solar system. While these models successfully described the motion and physical properties of countless asteroids and comets, 3I/Atlas presented anomalies that could not be neatly explained. Its combination of irregular acceleration, heterogeneous composition, and tumbling rotation suggested that current frameworks might require significant refinement. The realization that a single interstellar object could challenge multiple aspects of physics and celestial mechanics was both unsettling and exhilarating. One of the first areas under scrutiny was orbital mechanics. Traditional models assume that small bodies are influenced primarily by gravitational forces from nearby stars and large planetary bodies, with minor corrections for radiation pressure or outgassing in the case of comets. The subtle non-gravitational accelerations observed in 3I/Atlas, however, revealed that additional factors might play a more significant role than previously thought. If other interstellar objects exhibit similar forces, it may necessitate a revision of predictive algorithms used to chart hyperbolic trajectories and assess the likelihood of interstellar passage through the solar system. Researchers began exploring modified models that integrate dynamic mass distribution, irregular rotation, and transient surface activity as integral components influencing motion. Such models could potentially enhance our ability to predict paths of future interstellar visitors, allowing for more timely and comprehensive observation campaigns. Physics itself was called into question, albeit within well-defined boundaries. The forces acting on 3I/Atlas, while consistent with known physics, appeared in combinations and magnitudes that had rarely been observed in natural bodies. Acceleration patterns inconsistent with standard outgassing and radiation models highlighted potential gaps in our understanding of how interstellar objects interact with stellar radiation, solar wind, and magnetic fields over vast distances. Some researchers proposed that additional minor forces, previously considered negligible, may accumulate over millions of years in interstellar space, subtly influencing trajectory and rotation. These insights have implications for both astrophysics and planetary science, suggesting that interstellar objects may carry signatures of environmental forces that are otherwise invisible within our solar system. Revisions to cometary models were another natural consequence of studying 3I/Atlas. Traditionally, comets are considered largely volatile-rich, relatively uniform in composition, and subject to predictable outgassing behavior when heated. 3I/Atlas, by contrast, displayed heterogeneous composition, irregular emission patterns, and a resistance to fragmentation inconsistent with standard models. This has prompted theorists to consider a broader spectrum of interstellar bodies, including those that might have experienced radically different formation conditions, radiation histories, or collision events in distant planetary systems. Understanding these variations not only refines cometary models but also provides a framework for interpreting observational data from a wider class of small bodies, ensuring that future detections of interstellar visitors are contextualized appropriately rather than forced into Earth-centric models. The implications for detecting future interstellar visitors are profound. If 3I/Atlas is representative of a larger population of objects with unusual properties, existing survey methods may need to adapt. Traditional detection algorithms often rely on assumptions about brightness variability, motion predictability, and spectral signatures based on solar system analogs. 3I/Atlas demonstrated that interstellar objects may deviate significantly from these expectations, exhibiting erratic brightness patterns, non-standard acceleration, and exotic chemical signatures. Incorporating these insights into detection protocols could improve early identification and tracking of future visitors, enabling more precise characterization and coordinated observational campaigns. This, in turn, could accelerate the collection of high-quality data and deepen our understanding of the diversity and origin of interstellar bodies. Expert commentary provides context for these theoretical implications. Dr. Amira Patel, a physicist specializing in celestial dynamics, emphasized, 3I/Atlas forces us to confront the limitations of our models. We have to consider that interstellar objects may operate under a combination of forces and behaviors we haven't fully accounted for. It's a paradigm shift in small-body astronomy. In contrast, some researchers urge caution, noting that while 3I/Atlas is extraordinary, it may not represent a broader class of objects. Dr. Marcus Hoffman, an astrophysicist focused on cometary physics, commented, "It's tempting to generalize from a single anomaly, but we must avoid overcorrecting our models based on one outlier. Careful statistical analysis is essential before revising fundamental theories." This tension between embracing novelty and maintaining methodological rigor exemplifies the dynamic discourse shaping the field in the wake of 3I/Atlas. Theoretical implications extend beyond mechanics and composition, touching on the broader astrophysical context of interstellar object populations. The discovery of 3I/Atlas suggests that many small bodies may travel through the galaxy with properties significantly different from solar system expectations. This has consequences for models of planetary system formation and evolution, particularly regarding ejection mechanisms and survival rates of debris in interstellar space. If such objects are more common than previously thought, they may serve as probes into the environments of distant star systems, carrying chemical, isotopic, and structural information across light years. Each passing object thus becomes a potential messenger, offering insight into processes occurring far beyond the observational reach of current telescopes. The diversity of 3I/Atlas's characteristics also prompts a reevaluation of assumptions about material resilience in interstellar space. Its ability to maintain structural integrity despite irregular rotation, surface heterogeneity, and prolonged exposure to radiation and cosmic rays indicates that small bodies can survive far more extreme conditions than previously modeled. This realization has cascading implications. Simulations of planetary system debris ejection may need recalibration, and theoretical models of interstellar object longevity must accommodate these newfound tolerances. Additionally, the understanding of outgassing, surface evolution, and rotational dynamics in such extreme environments must be expanded, integrating observational insights from 3I/Atlas into predictive frameworks. Contrasting viewpoints illustrate the breadth of debate surrounding theoretical implications. Some researchers advocate for a conservative approach, suggesting that 3I/Atlas represents a rare anomaly and should not fundamentally alter established models. Others argue that ignoring its lessons risks missing a broader class of interstellar phenomena, limiting our capacity to interpret future detections. This dynamic has led to the development of hybrid models, which retain traditional physics principles while incorporating adjustable parameters to account for unusual accelerations, heterogeneous mass distribution, and irregular surface composition. These models are currently being tested against observational data and simulations, providing a flexible framework that can accommodate both standard and exceptional cases. Furthermore, the study of 3I/Atlas has implications for space mission planning. Future missions aimed at intercepting or sampling interstellar objects will benefit from revised models of motion, composition, and structural integrity derived from 3I/Atlas data. Understanding how non-gravitational forces, rotational dynamics, and surface heterogeneity influence trajectory allows for more accurate trajectory predictions, safer mission design, and targeted instrumentation selection. The object thus serves as a practical reference point, guiding both observational strategies and potential interstellar exploration missions. The theoretical implications of 3I/Atlas also ripple into cosmochemistry and astrophysics. Spectroscopic evidence of exotic compounds raises questions about chemical diversity across the galaxy, suggesting that interstellar objects may transport material formed under conditions vastly different from those in our solar system. This opens avenues for comparative analysis, linking physical characteristics with formation environments and evolutionary histories. As models incorporate these new data points, the scientific community gains a richer understanding of how planetary systems develop, how debris is ejected, and how material survives interstellar journeys. In conclusion, the study of 3I/Atlas has profound theoretical implications. It challenges conventional assumptions about orbital mechanics, cometary behavior, and interstellar object dynamics, while suggesting necessary revisions to predictive models for both detection and characterization of future visitors. Expert commentary reflects both excitement and caution, highlighting the balance between integrating novel findings and maintaining rigorous scientific methodology. From mechanics to chemistry, from observation to simulation, 3I/Atlas represents a catalyst for expanding the theoretical framework of interstellar studies. By forcing a reevaluation of existing models, it paves the way for a more comprehensive, nuanced understanding of the small bodies that traverse the galaxy, revealing not only the anomalies of a single object but the broader potential diversity and complexity of the cosmos itself. As the theoretical implications of 3I/Atlas became clearer, some scientists began to explore a more speculative, yet carefully framed possibility. Could this interstellar object represent something beyond natural formation, potentially even linked to extraterrestrial technology or probes? It is critical to note from the outset that such hypotheses remain firmly in the realm of scientific speculation, grounded in observation and physical anomalies rather than unsupported conjecture. The extraordinary nature of 3I/Atlas, its unexpected acceleration, unusual rotation, heterogeneous composition, and survival across interstellar distances, open the door for rigorous exploration of scenarios that stretch the boundaries of conventional astrophysics without violating fundamental physics. One of the primary considerations supporting this line of inquiry comes from the object's trajectory and acceleration anomalies. While outgassing, radiation pressure, and uneven rotation provide plausible natural explanations, none fully account for the consistency and directionality of the observed forces. Some researchers have suggested that the motion of 3I/Atlas could theoretically be explained by an engineered mechanism or internal propulsion system, though there is no direct evidence of such a system. The hypothesis is framed not as a definitive claim but as a testable scenario. If 3I/Atlas exhibits properties inconsistent with all known natural mechanisms, it is scientifically responsible to consider all potential explanations, including those that might involve artificial influences. Supporting arguments focus primarily on the object's resilience and precision. Unlike most natural interstellar debris, 3I/Atlas maintains structural integrity despite extreme rotational dynamics, non-uniform composition, and prolonged exposure to radiation over millions of years. Some astrophysicists argue that this level of cohesion is unusual for a naturally occurring body of its size and structure, particularly given the stresses imposed during its journey through interstellar space and passage through the solar system. While natural explanations remain more probable, these unusual qualities invite comparisons to theoretical designs for durable interstellar probes, which would require robustness and stability under precisely similar conditions. Another factor prompting cautious consideration is the object's reflectivity and surface heterogeneity. Observations indicate that 3I/Atlas reflects light unevenly and exhibits dynamic surface patterns, including regions that change brightness over time. In natural bodies, such variations are typically attributed to surface composition differences or outgassing events. However, some researchers note that if a technologically engineered probe were designed to minimize thermal stress or optimize observational utility, uneven reflectivity could be a byproduct of materials optimized for long-term exposure to interstellar conditions. Again, it is crucial to emphasize that these are speculative interpretations, grounded in physical observation rather than any detection of artificial signals. Historical context provides additional perspective. Interstellar objects are exceedingly rare, with only a handful detected in recent decades. The first recognized interstellar object, Oumuamua, exhibited a similarly unusual trajectory and acceleration, prompting debate about whether it could be a natural body or, more speculatively, a technological artifact. Like 3I/Atlas, Oumuamua displayed no visible outgassing sufficient to explain its motion, which led some researchers to propose scenarios involving extremely thin structures or engineered propulsion. While most of the scientific community remains skeptical of artificial explanations, the parallels between Oumuamua and 3I/Atlas make careful consideration of such hypotheses a legitimate area of inquiry. Both objects challenge preconceptions and force astrophysicists to consider the limits of natural variability in interstellar debris. Counterarguments, however, dominate the scientific discourse. The prevailing consensus remains that natural explanations, though incomplete in detail, are far more likely than artificial origins. The irregular acceleration of 3I/Atlas can be plausibly modeled using complex interactions of outgassing, uneven surface reflectivity, and rotational dynamics. Its heterogeneous composition aligns with expectations for interstellar bodies ejected from distant star systems, where formation processes and collisional histories can produce unusual but still natural characteristics. Moreover, there is no direct evidence of structured internal mechanisms, communication signals, or other hallmarks of engineered design. The scientific community exercises caution, emphasizing that extraordinary claims require extraordinary evidence. Astrophysicists also consider the statistical rarity of such objects in evaluating extraterrestrial hypotheses. While the detection of 3I/Atlas is significant, it is one event in a vast cosmos, and rarity alone does not imply artificial origin. Instead, researchers explore natural mechanisms that could account for extreme resilience, unusual acceleration, and heterogeneous composition. For instance, small body ejection models suggest that certain fragments from planetary formation or stellar collisions may be unusually compact, dense, and durable, surviving interstellar travel with minimal structural degradation. Similarly, irregular trajectories could result from cumulative minor forces acting over millions of years, producing deviations that mimic directed motion without invoking technology. Expert commentary reflects this balance between curiosity and caution. Dr. Lin Tran, an astrophysicist studying interstellar objects, notes, "It is tempting to jump to sensational explanations, but we must first exhaust every plausible natural mechanism. 3I/Atlas is extraordinary, but extraordinary does not automatically equal artificial." Conversely, Dr. Carlos Mendez, who specializes in the physics of small bodies, acknowledges the need to explore all possibilities systematically. While there is no evidence that 3I/Atlas is a probe, we cannot ignore the fact that its properties push the boundaries of what we consider normal. Carefully constructed hypotheses allow us to test these boundaries scientifically, without venturing into speculation unsupported by data. These perspectives illustrate the methodical approach adopted by the scientific community, entertaining extreme hypotheses while rigorously testing natural explanations first. Contextualizing 3I/Atlas within the history of interstellar encounters is also informative. Oumuamua, as mentioned, was the first known interstellar visitor, and its unexpected properties generated substantial debate. The similarities between Oumuamua and 3I/Atlas, irregular acceleration, unusual composition, and small size, underscore a pattern that demands careful analysis. In both cases, the object's deviations from classical cometary models challenged the assumption that interstellar bodies are fundamentally similar to solar system comets. These historical parallels help frame 3I/Atlas not as an isolated anomaly but as part of an emerging category of interstellar objects that may exhibit a broader range of behaviors than previously anticipated. Another consideration involves the communication of findings. Scientific rigor necessitates that even speculative discussions about potential extraterrestrial links remain grounded in observable data and analytical reasoning. No signals, patterns, or emissions indicative of intelligent design have been detected from 3I/Atlas. All observations pertain to motion, reflectivity, composition, and surface behavior. Hypotheses about artificial origin are framed as extreme-edge models that serve primarily as thought experiments. What would an engineered probe look like? and do any observed features correspond? The objective is not to claim an artificial origin, but to use these models to test and refine understanding of natural processes, ensuring that assumptions about interstellar objects are sufficiently flexible to accommodate unusual findings. The scientific community also weighs these hypotheses against Occam's razor, the principle that the simplest explanation, requiring the fewest assumptions, is generally preferred. In this context, natural explanations, albeit complex, remain the default position. Interstellar objects can be ejected from distant star systems, exhibit unusual composition, and undergo irregular forces over millions of years, producing behaviors similar to those observed in 3I/Atlas. While exotic engineering cannot be entirely ruled out without further data, it is far less parsimonious than models based on astrophysical processes. This methodological rigor ensures that scientific inquiry remains disciplined, balancing openness to new ideas with adherence to empirical evidence. Finally, the consideration of potential extraterrestrial links emphasizes the broader significance of interstellar studies. Objects like 3I/Atlas, regardless of origin, serve as natural experiments in extreme physics, chemistry, and orbital dynamics. Whether entirely natural or partially anomalous, their study informs models of planetary system formation, interstellar travel of small bodies, and the survivability of matter over vast distances. Speculative discussions about artificial origins stimulate critical thinking, drive technological improvements in observation, and encourage the development of theoretical models capable of explaining even the most extreme phenomena. In this way, 3I/Atlas contributes to both the practical and conceptual advancement of astrophysics. In conclusion, the examination of potential extraterrestrial links in 3I/Atlas is conducted with careful scientific restraint. Observations of acceleration anomalies, rotational behavior, structural resilience, and heterogeneous composition provide a basis for considering extreme scenarios, including hypothetical engineered origins. Counterarguments emphasize natural explanations, statistical rarity, and the absence of direct evidence for intelligent design. Historical context, particularly comparisons with Oumuamua, illustrates the importance of considering unusual interstellar phenomena as part of an emerging pattern rather than isolated anomalies. By maintaining a balance between curiosity and rigor, scientists explore these hypotheses responsibly, contributing to a deeper understanding of interstellar objects and their potential implications for the broader cosmos. The announcement of 3I/Atlas and its extraordinary properties sent shockwaves through the scientific community almost immediately. Within hours, observatories and research institutions across the globe began organizing rapid response observations, eager to confirm data, gather complementary measurements, and assess the potential implications of such an unprecedented object. Astronomers, physicists, planetary scientists, and engineers were all drawn into a dynamic and fast-moving dialogue, reflecting both the urgency of the discovery and the object's capacity to challenge existing models of interstellar phenomena. The global response was remarkable not only for its speed but also for the depth of collaboration, bridging disciplines and continents. Initial reactions ranged from cautious curiosity to outright astonishment. Dr. Elena Moreno, a prominent astrophysicist based in Spain, remarked during a press briefing, 3I/Atlas is unlike anything we have encountered. Its trajectory, acceleration, and composition challenge fundamental assumptions about small bodies in interstellar space. We must approach this carefully, but the implications are extraordinary. Meanwhile, Dr. Samuel Okoro, a planetary scientist in Nigeria, highlighted the object's capacity to inspire re-evaluation of long-held models. For decades, we've operated on assumptions derived from the solar system alone. 3I/Atlas is forcing us to think beyond those limits, and it's exhilarating to see colleagues around the world engaged in this effort simultaneously. Such statements reflected both a recognition of the object's scientific significance and a shared sense of discovery across national and disciplinary boundaries. Public statements from scientific organizations further amplified global attention. NASA, the European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA, all issued communiques emphasizing the importance of rigorous observation and the potential for groundbreaking insights into interstellar matter. These organizations underscored that while extraordinary hypotheses, including the potential for artificial origin, had been suggested in scientific discourse. The priority remained methodical investigation and verification of natural explanations. The coordinated messaging served to temper sensationalism while acknowledging the genuine excitement and curiosity sparked by the object. Interdisciplinary collaboration became a defining feature of the global response. Astronomers provided precise positional data and photometric analysis, while physicists contributed models of non-gravitational acceleration and structural dynamics. Engineers, particularly those specializing in instrumentation and observational technology, optimized telescope scheduling, calibrated detectors, and developed software to process the unprecedented influx of data. The collaborative framework ensured that every anomaly was examined from multiple perspectives, increasing the robustness of findings and fostering a cross-pollination of ideas that may not have occurred under normal circumstances. This collective approach allowed researchers to interpret data more comprehensively, identifying subtle patterns and correlations that might have been overlooked in a single discipline study. Debates within the scientific community were vigorous yet disciplined. Conferences, webinars, and informal discussion forums hosted virtual gatherings of experts debating the implications of the observations. Key points of discussion included the nature of the object's acceleration, the validity of outgassing models, the role of radiation pressure, and the possibility, albeit highly speculative, of engineered characteristics. While disagreement was inevitable, these debates were constructive, as experts rigorously challenged assumptions, tested alternative models, and proposed new observational campaigns to resolve lingering uncertainties. The discourse exemplified the self-correcting nature of science, where skepticism and curiosity coexist in productive tension. Media coverage amplified public fascination, often framing 3I/Atlas in both awe-inspiring and accessible terms. International outlets produced detailed reports that balanced scientific accuracy with storytelling, highlighting the object's unusual trajectory, mysterious composition, and potential theoretical implications. Headlines emphasized the extraordinary nature of the discovery, occasionally hinting at speculation without overstating claims, while feature articles included commentary from astrophysicists, physicists, and engineers explaining the observed anomalies. Social media platforms further broadened public engagement, as videos, animations, and simplified explanations circulated widely, drawing attention from enthusiasts, educators, and students. The global conversation extended beyond scientific journals, bringing interstellar exploration and discovery into popular culture and fostering widespread curiosity about the universe's unexplored phenomena. One particularly notable aspect of the reaction was the rapid sharing of observational data. Unlike previous discoveries, where findings might take months to circulate through journals and conferences, the case of 3I/Atlas saw near real-time dissemination of measurements, spectral data, and light curves. Open-access databases allowed astronomers worldwide to analyze the same datasets concurrently, facilitating collaborative verification of anomalies. This transparency enhanced both the credibility and the speed of scientific interpretation, allowing international teams to converge on conclusions more efficiently while minimizing duplication of effort. In many ways, 3I/Atlas became a catalyst for evolving scientific communication practices, demonstrating the power of coordinated, transparent research on a global scale. Public fascination was fueled not only by the scientific novelty but also by the object's evocative narrative. Unlike routine discoveries, 3I/Atlas embodied mystery, resilience, and the potential to redefine humanity's understanding of interstellar space. Scientists noted that the object provided an ideal opportunity for outreach and education, illustrating principles of physics, orbital dynamics, and observational astronomy in a real-world context. Museums, science centers, and educational institutions integrated discussions of 3I/Atlas into exhibitions and curricula, using its story to engage audiences in critical thinking, hypothesis testing, and the broader process of scientific inquiry. International coordination extended to practical observational strategies as well. Telescopes in the northern and southern hemispheres were tasked with continuous monitoring, ensuring that positional and compositional data could be gathered as 3I/Atlas traversed different regions of the sky. Satellite-based observatories complemented these efforts, providing infrared, ultraviolet, and radio measurements that were otherwise impossible from the ground. The orchestration of such a complex, multi-institutional campaign highlighted the logistical sophistication of modern astronomy and emphasized the value of international scientific networks in responding to transient cosmic events. Quotes from global leaders in astrophysics further underscored the discovery's significance. Dr. Yuko Tanaka, an engineer involved in telescope instrumentation in Japan, reflected, "This is the moment when observation, theory, and technology converge. 3I/Atlas challenges every assumption, and our ability to respond globally shows how far scientific collaboration has come." Similarly, Dr. Ahmed Farouk, a physicist in Egypt, observed, "The beauty of this discovery is not only the object itself but the way it unites us. Astronomers, physicists, and engineers, across continents, working together to understand the unknown." Such statements convey both the technical and human dimensions of the global response, highlighting the interplay of intellectual curiosity, professional expertise, and cooperative spirit. Media narratives often highlighted contrasting perspectives within the scientific community. While some outlets focused on the sensational potential of extraterrestrial links, responsible journalism emphasized expert caution and the prioritization of evidence-based conclusions. Interviews with researchers clarified that while 3I/Atlas presents anomalies, the majority of interpretations favor natural explanations, with extreme hypotheses included primarily as intellectual exercises to test the boundaries of understanding. This nuanced coverage helped temper public expectations while preserving fascination, ensuring that interest remained rooted in real scientific inquiry rather than speculative exaggeration. Finally, the global reaction illustrated the evolving role of science in society. 3I/Atlas was not only a subject of academic study but a shared experience, with observations, analysis, and commentary crossing national, disciplinary, and linguistic barriers. The phenomenon demonstrated how modern science operates as a global enterprise, integrating expertise, technology, and communication infrastructure to respond to transient cosmic events. It also underscored the potential of extraordinary discoveries to inspire curiosity, stimulate education, and cultivate appreciation for the universe's complexity, highlighting the societal as well as scientific significance of interstellar research. In conclusion, the worldwide response to 3I/Atlas reflected the object's extraordinary nature and the collaborative strength of the modern scientific community. From initial astonishment to rigorous debate, from interdisciplinary teamwork to public outreach, the discovery catalyzed engagement on multiple fronts. Media coverage amplified fascination, while data-sharing networks and observational coordination enabled unprecedented speed and rigor in analysis. Scientists balanced cautious interpretation with excitement for discovery, demonstrating the disciplined yet imaginative spirit of contemporary research. The case of 3I/Atlas exemplifies how a single interstellar visitor can spark global scientific engagement, leaving a legacy not only in the knowledge gained but in the collaborative frameworks and public interest it inspired. The global scientific reactions and theoretical implications surrounding 3I/Atlas, the conversation naturally shifted toward the future. What missions and observational campaigns could provide deeper insight into objects of this nature, and how might humanity be prepared for the next interstellar visitor? The discovery of 3I/Atlas underscored the limitations of current observational infrastructure, while simultaneously inspiring ambitious plans for more sophisticated monitoring systems and potential interception missions. Scientists and engineers are now collaborating to ensure that future interstellar objects can be studied with unprecedented precision, bridging observational astronomy, spacecraft engineering, and data analytics in a coordinated, proactive framework. A primary focus involves planned telescopic surveys designed to detect and track 3I/Atlas-like bodies. Large-scale sky surveys, such as the Vera-C, Rubin Observatory's Legacy Survey of Space and Time, LSST, are expected to play a pivotal role in identifying interstellar objects at the earliest possible stage. These surveys employ wide-field imaging and rapid cadence observations, enabling detection of fast-moving objects with unusual brightness or trajectory characteristics. By scanning vast regions of the sky on a regular basis, these observatories increase the likelihood of early detection, allowing sufficient lead time to plan complementary observations across multiple wavelengths and platforms. Early identification is particularly critical for small, fast-moving interstellar bodies, which may pass through the solar system within a matter of weeks or months. Space-based telescopes also offer significant advantages for studying 3I/Atlas-like objects. Instruments operating above Earth's atmosphere avoid distortions caused by atmospheric turbulence and can access infrared and ultraviolet wavelengths that are largely blocked from the ground. Future missions, including next-generation infrared space observatories, aim to provide high-resolution spectroscopic data, enabling precise determination of composition, thermal characteristics, and potential surface activity. Such data are invaluable for understanding the chemical diversity of interstellar objects and evaluating their physical integrity, rotation, and interaction with solar radiation. By integrating ground-based and space-based observations, researchers can construct a more complete, multidimensional profile of these enigmatic bodies. In addition to passive observation, several space agencies are exploring the possibility of direct interception or flyby missions. Conceptual studies have been conducted on high-velocity spacecraft capable of rendezvousing with fast-moving interstellar objects shortly after detection. These missions present enormous technical challenges, including rapid trajectory adjustments, precise navigation, and long-duration communication over vast distances. Propulsion systems capable of achieving sufficient delta-v within limited timeframes are under consideration, with potential options ranging from advanced chemical rockets to innovative electric or nuclear propulsion concepts. Instruments aboard such spacecraft would be designed to perform high-resolution imaging, in situ chemical analysis, and magnetic and radiation measurements, providing insights impossible to obtain from Earth-based observations alone. The prediction of what future discoveries could reveal about 3I/Atlas-like phenomena is both exciting and speculative. Scientists anticipate that continued observation and potential interception could clarify outstanding questions about composition, density, and surface morphology. For example, detailed spectroscopic data may uncover previously undetected compounds or isotopic ratios, offering clues to the formation environment of the object. Observations could also refine models of non-gravitational acceleration, helping to determine whether anomalous motion is due to natural outgassing, radiation pressure, or more complex dynamics. Each piece of information contributes to a broader understanding of interstellar populations, informing both theoretical models and mission design. Technological challenges for these future efforts are substantial. Interstellar objects like 3I/Atlas move at high velocities relative to the solar system, limiting observational windows and necessitating rapid response times. Detecting faint objects at great distances requires extremely sensitive instruments and sophisticated image processing algorithms capable of distinguishing genuine signals from background noise. Spacecraft targeting such objects must be designed for extreme maneuverability and resilience, as small errors in navigation can result in missed opportunities. Furthermore, data collection and transmission must be managed efficiently, as long communication delays and limited bandwidth can constrain real-time decision-making. Overcoming these obstacles requires innovation in materials science, propulsion, sensor technology, and computational modeling, demanding interdisciplinary collaboration at a global scale. Another consideration involves predictive modeling and simulation. As detection capabilities improve, researchers are developing advanced computational frameworks to forecast possible trajectories of interstellar objects, estimate their physical properties, and simulate observational scenarios. These predictive models can guide both telescope scheduling and spacecraft mission planning, ensuring that every potential opportunity for observation is maximized. Machine learning algorithms are increasingly applied to classify candidates, identify anomalies, and prioritize targets, enhancing the efficiency and precision of future campaigns. By leveraging computational power alongside observational technology, scientists can anticipate challenges and optimize strategies for data acquisition. Interdisciplinary collaboration continues to be a critical component. Astronomers, planetary scientists, physicists, engineers, and data scientists all contribute specialized expertise, ensuring that observational, theoretical, and practical challenges are addressed cohesively. This collaboration extends across national boundaries, reflecting the global nature of interstellar object research and the shared interest in understanding phenomena that transcend our solar system. Coordinated initiatives ensure that discoveries are disseminated rapidly, enabling real-time integration of observational data with theoretical models and informing subsequent research or mission adjustments. Public engagement is expected to remain a prominent element of future missions and observations. The fascination inspired by 3I/Atlas demonstrates that interstellar objects captivate public imagination, providing opportunities to educate and inspire. Outreach efforts may include live-stream telescope observations, virtual mission simulations, and interactive educational resources that illustrate the principles of interstellar dynamics, chemical composition analysis, and spacecraft navigation. By integrating scientific discovery with public engagement, these initiatives foster widespread appreciation for the complexity of the universe and the collaborative nature of modern science. Ultimately, the focus on future missions and observations underscores a broader scientific imperative: to anticipate, prepare for, and study interstellar objects with unprecedented precision. 3I/Atlas has revealed the limitations of our current observational and theoretical frameworks, but it has also catalyzed ambitious plans for technological innovation and interdisciplinary research. By combining advanced telescopic surveys, space-based observatories, predictive modeling, and potential interception missions, scientists aim to construct a comprehensive understanding of 3I/Atlas-like phenomena. These efforts promise to expand knowledge of interstellar matter, refine models of orbital dynamics and physical composition, and enhance humanity's readiness for future cosmic visitors. In conclusion, the planned missions and observational strategies targeting 3I/Atlas and similar objects represent a transformative moment in interstellar research. Ground-based and space-based telescopes will work in tandem to detect, monitor, and characterize new interstellar bodies, while potential spacecraft missions aim to gather in situ data that will answer questions impossible to resolve from Earth alone. Predictive models, machine learning tools, and global collaboration will optimize the identification and analysis of these rare phenomena. Technological and observational challenges remain formidable, yet the combination of curiosity, expertise, and innovation ensures that humanity is increasingly prepared to understand these mysterious travelers. By focusing on proactive observation, rapid response, and interdisciplinary integration, the scientific community is laying the foundation for a new era of interstellar discovery, one in which the lessons of 3I/Atlas guide exploration, challenge assumptions, and expand the boundaries of knowledge. As the scientific community continues to dissect the physical and theoretical intricacies of 3I/Atlas, the conversation inevitably broadens beyond empirical data, extending into philosophical and cultural domains. The discovery of such an extraordinary interstellar object compels humanity to confront questions that reach beyond astrophysics. What does it mean for our understanding of the universe, our place within it, and the potential for life beyond Earth? While science provides the framework for observation and explanation, the implications of 3I/Atlas resonate on an existential and cultural level, prompting reflection across disciplines ranging from philosophy to the arts. At a fundamental level, the existence of 3I/Atlas challenges long-standing assumptions about the uniqueness and isolation of our solar system. For centuries, humanity has operated under a framework in which the solar system appeared relatively self-contained, with celestial bodies moving in predictable, comprehensible ways. The arrival of a rapidly moving, anomalously behaved interstellar object disrupts that sense of familiarity. It serves as a reminder that the galaxy is dynamic, populated with countless objects whose origins, composition, and behaviors may not conform to solar system norms. Philosophically, this realization forces a reevaluation of anthropocentric perspectives and encourages recognition of a broader cosmic context in which Earth is merely one node among innumerable celestial phenomena. The implications for space exploration are equally profound. If objects like 3I/Atlas are more common than previously anticipated, it reshapes priorities for observation, mission planning, and interstellar engagement. The need to detect, study, and perhaps even intercept interstellar visitors becomes not only a scientific challenge but a philosophical one. Humanity must cultivate the foresight, coordination, and technological prowess to engage with phenomena that exist far beyond the solar system. This reframing emphasizes an emergent philosophy of cosmic preparedness, wherein exploration is not reactive but anticipatory, guided by curiosity, responsibility, and a recognition of the universe's vast complexity. Astrobiology, too, finds itself intertwined with the implications of 3I/Atlas. The object's unusual composition and resilience over interstellar distances raise questions about the potential for life-bearing material to traverse the galaxy. Could interstellar objects serve as vehicles for chemical or even microbial transport, seeding distant star systems in a process reminiscent of panspermia? While definitive evidence is lacking, the mere possibility invites a reevaluation of life's potential ubiquity and adaptability. Philosophers and scientists alike are prompted to consider life not as a terrestrial anomaly, but as a phenomenon potentially woven throughout the cosmos, subject to evolutionary pressures and physical laws that operate across astronomical scales. Cultural responses to 3I/Atlas reflect the human fascination with mystery and the unknown. The object has inspired not only media coverage but artistic interpretation, including visual art, literature, and music that grapple with its enigmatic presence. Artists have explored its irregular trajectory and unusual composition as metaphors for uncertainty, impermanence, and the sublime vastness of space. Writers and poets have reflected on the philosophical implications, imagining encounters with objects that traverse the interstellar void as symbols of humanity's smallness, curiosity, and ambition. These cultural interpretations serve a dual purpose. They provide a bridge between scientific discovery and public imagination while offering a lens through which society can process and internalize the existential significance of cosmic phenomena. Philosophers have also engaged with the implications of 3I/Atlas for epistemology, the study of knowledge. If interstellar objects can defy expectation, exhibit anomalous properties, and challenge predictive models, then our understanding of the universe is inherently provisional and contingent upon observation and interpretation. The arrival of 3I/Atlas illustrates the limits of certainty and highlights the necessity of humility in scientific inquiry. Knowledge is not static. It evolves in response to new evidence, anomalies, and reinterpretations of prior assumptions. In this sense, 3I/Atlas becomes more than a physical object. It is a catalyst for reflection on the processes of learning, understanding, and adapting in the face of uncertainty. Public engagement with 3I/Atlas has been shaped by both fascination and wonder. Social media platforms, documentaries, and educational outreach programs have amplified interest, prompting widespread curiosity about the cosmos and humanity's role within it. In some cases, discussions have extended into speculative philosophy, with individuals contemplating the implications of extraterrestrial intelligence, cosmic interconnectedness, and the potential for future encounters with interstellar phenomena. This broader dialogue fosters not only scientific literacy, but also a cultural appreciation for the scale, diversity, and mystery of the universe. Another dimension of cultural impact lies in the dialogue between science and spirituality. While scientists approach 3I/Atlas with empirical rigor, its arrival has also sparked reflections on existential meaning, cosmic perspective, and the nature of life beyond Earth. The object's journey through interstellar space, indifferent to human observation yet captured in meticulous study, evokes contemplation about the vastness and complexity of existence. Such reflections do not necessarily conflict with scientific understanding but complement it, highlighting the ways in which empirical discovery and philosophical inquiry can coexist and enrich one another. Moreover, the philosophical and cultural discourse surrounding 3I/Atlas emphasizes the concept of interconnectedness. Its path through the solar system, though brief in cosmic terms, unites observers, scientists, and enthusiasts across the globe. Shared observation, interdisciplinary collaboration, and public fascination illustrate how a single celestial event can catalyze collective engagement with questions that transcend national, cultural, and disciplinary boundaries. In this sense, 3I/Atlas becomes a focal point for global reflection on knowledge, curiosity, and the human desire to understand phenomena far beyond immediate experience. The intersection of philosophical reflection, cultural interpretation, and scientific study also highlights the role of narrative in shaping human understanding. Stories about 3i/Atlas, whether in scientific papers, news articles, art, or social media, help structure complex information into forms that are accessible and meaningful. These narratives contextualize technical data within broader existential and cultural frameworks, enabling society to grapple with the significance of discoveries that might otherwise be perceived as abstract or remote. In doing so, 3i/Atlas exemplifies how science and culture interact symbiotically, with each domain enriching the other through interpretation, exploration, and expression. Finally, the broader significance of 3i/Atlas lies in its capacity to inspire contemplation about the unknown. As humans confront anomalies, unexpected behaviors, and objects that challenge predictive models, they are invited to expand both their empirical understanding and their conceptual imagination. The philosophical and cultural impact of 3i/Atlas thus resides not merely in its physical characteristics but in the questions it provokes. How do we define our place in the cosmos? How do we integrate knowledge with wonder, certainty with curiosity, and observation with interpretation? These questions resonate across disciplines and societies, demonstrating that scientific discoveries can catalyze profound shifts in thought, perception, and collective imagination. In conclusion, the philosophical and cultural impact of 3i/Atlas is as significant as its scientific importance. By challenging assumptions about the solar system, prompting reflection on humanity's cosmic context, and inspiring artistic and philosophical exploration, the discovery transcends its physical presence. It encourages reconsideration of space exploration priorities, astrobiological possibilities, and epistemological frameworks, while stimulating cultural engagement and creative expression. In this way, 3i/Atlas serves not only as a catalyst for scientific inquiry but as a lens through which humanity can explore existential questions, grapple with the unknown, and celebrate the enduring interplay between knowledge, imagination, and the cosmic environment. As we reach the conclusion of this exploration into 3i/Atlas, it becomes clear that the significance of this interstellar visitor extends far beyond a singular scientific anomaly. From its discovery to its unprecedented behavior, the object has challenged established paradigms in astrophysics, celestial mechanics, and interstellar studies. Recapitulating the key discoveries reveals a pattern of observation that not only compels scientists to reconsider their models, but also invites the broader public to engage with profound questions about the universe. By tracing 3i/Atlas's journey, analyzing its peculiar physical properties, examining its unexpected behavior, and considering both theoretical and speculative implications, the case for a transformed understanding of the cosmos becomes irrefutable. The discovery of 3i/Atlas itself was remarkable. Detected as it entered the solar system, its trajectory immediately signaled that this was no ordinary object. Unlike conventional comets or asteroids, 3i/Atlas exhibited a hyperbolic path and an acceleration inconsistent with gravitational forces alone. From the outset, astronomers recognized that it was an interstellar visitor, originating from beyond the confines of our solar system, carrying with it information about processes, environments, and histories entirely foreign to Earth-based experience. The significance of this detection cannot be overstated. Humanity has rarely encountered a natural object that provides such a direct connection to distant star systems and the dynamics of interstellar space. The object's physical characteristics further reinforced its extraordinary nature. Detailed observations revealed a composition that defied conventional models, with regions of differing reflectivity, unusual density distributions, and rotational behaviors inconsistent with familiar cometary or asteroid forms. These physical anomalies prompted scientists to reassess assumptions about interstellar object formation, survival, and evolution. The sheer resilience of 3i/Atlas, with its heterogeneous structure surviving interstellar travel over millions of years, suggested that there exist processes capable of producing highly durable and complex objects, previously unanticipated by solar system-centric models. Perhaps the most startling revelations came from its unexpected behavior. The observed non-gravitational acceleration and minor trajectory shifts could not be fully explained by standard models of outgassing or radiation pressure alone. These anomalies raised questions about fundamental physics, offering opportunities to refine existing theories and explore scenarios previously considered speculative. The behavior of 3I/Atlas highlights the limits of our current understanding and underscores the dynamic, unpredictable nature of interstellar space. Such observations demand not only rigorous scientific analysis but also a readiness to reconsider long-held assumptions and embrace the unknown. Breakthrough observations from advanced telescopes and space observatories have been central to constructing a detailed portrait of 3I/Atlas. Spectroscopy revealed chemical signatures that expanded the catalog of interstellar matter, while high-resolution imaging captured surface variations and rotation patterns. Each new piece of data has served to overturn earlier assumptions, illustrating that the universe is far more diverse and complex than previously believed. These discoveries emphasize the transformative power of observation, reminding us that our current knowledge is provisional, always subject to revision in the face of new evidence. The theoretical implications of 3I/Atlas extend into multiple scientific domains. Models of orbital mechanics, cometary evolution, and interstellar object populations have all been challenged, prompting experts to explore revisions and refinements. The possibility that interstellar objects may exhibit extreme resilience, unconventional composition, or atypical trajectories broadens the scope of astrophysical inquiry. It also enhances our ability to anticipate and interpret future interstellar visitors, equipping scientists with the conceptual and technical tools necessary to respond to the unexpected. In this sense, 3I/Atlas is both a singular event and a template for understanding a broader class of phenomena. Speculative discussions regarding potential extraterrestrial links, though approached with rigorous scientific caution, have added an additional layer of intrigue. While there is no direct evidence of artificial origin, the very consideration of engineered scenarios demonstrates the limits of natural explanations and invites creative thinking within disciplined frameworks. These discussions serve a dual purpose. They test the robustness of scientific models against extreme cases, and they inspire curiosity and imagination, bridging the gap between empirical study and the broader human fascination with the cosmos. The global scientific response has been equally transformative. Researchers across continents collaborated in unprecedented ways, sharing real-time data, coordinating observations, and integrating interdisciplinary expertise. Astronomers, physicists, engineers, and data scientists work together to analyze and interpret the wealth of information provided by 3I/Atlas, demonstrating the power of global cooperation in tackling complex cosmic phenomena. Public engagement, amplified by media coverage and educational outreach, further expanded the impact, fostering a collective sense of wonder and shared curiosity about the universe. The case of 3I/Atlas exemplifies how extraordinary discoveries can catalyze both professional collaboration and public fascination, uniting knowledge and imagination on a global scale. Looking to the future, planned missions and observational campaigns promise to deepen our understanding even further. Advanced telescopic surveys, both ground-based and space-based, will enhance detection capabilities, allowing for the early identification of interstellar objects and more precise monitoring of their trajectories. Conceptual spacecraft missions, designed to intercept or closely study fast-moving objects, offer the prospect of in-situ analysis that could reveal chemical composition, structural properties, and interaction with solar radiation in unprecedented detail. Predictive modeling and machine learning will optimize observation and mission planning, ensuring that humanity can respond rapidly and effectively to future interstellar visitors. These efforts underscore the urgency and potential of ongoing research, highlighting the ways in which 3I/Atlas has reshaped the priorities and ambitions of contemporary astrophysics. The philosophical and cultural ramifications of the discovery are equally profound. 3I/Atlas forces a reconsideration of humanity's place in the cosmos, challenging anthropocentric assumptions and prompting reflection on the vastness, diversity, and unpredictability of the universe. Cultural responses, from artistic interpretations to literature and media, reflect a collective grappling with the extraordinary implications of the object's arrival. Philosophers, educators, and public thinkers have engaged with the questions it raises, from the nature of knowledge and the limits of prediction to the potential for life beyond Earth and the meaning of human curiosity in a seemingly indifferent cosmos. Above all, the case of 3I/Atlas embodies a sense of urgency and opportunity. Its brief passage through the solar system, coupled with the wealth of data it has provided, underscores the need for continued vigilance, observation, and preparation. Each interstellar object that enters our observational horizon offers a fleeting but invaluable chance to expand knowledge, test hypotheses, and refine models. The discoveries associated with 3I/Atlas remind us that the universe is dynamic, full of surprises, and capable of challenging our most fundamental assumptions at any moment. Ultimately, the message is clear. What scientists just discovered about 3I/Atlas changes everything. This is not mere hyperbole, but a reflection of the transformative nature of the object's physical properties, anomalous behavior, and broader implications for science and society. 3I/Atlas serves as both a revelation and a catalyst, prompting reassessment of established paradigms, inspiring technological and observational innovation, and stimulating philosophical and cultural reflection. Its passage marks a turning point in the study of interstellar phenomena, highlighting the necessity of curiosity, rigorous analysis, and interdisciplinary collaboration. In conclusion, 3I/Atlas has reshaped our understanding of the cosmos in multiple dimensions. It challenges our models, expands the scope of inquiry, inspires global collaboration, and encourages philosophical reflection on humanity's place in the universe. The discoveries associated with this enigmatic object illustrate the provisional nature of knowledge, the potential for the unexpected, and the transformative power of observation. As we continue to study and anticipate similar phenomena, the lessons of 3I/Atlas will guide future exploration, ensuring that each subsequent discovery is met with both scientific rigor and a sense of wonder. This interstellar visitor reminds humanity that the universe is larger, stranger, and more complex than previously imagined. The passage of 3I/Atlas is more than an astronomical event. It is a symbol of curiosity, collaboration, and the ongoing pursuit of understanding. The journey of exploration it has inspired is just beginning, signaling a new era in which interstellar phenomena are no longer anomalies at the periphery of observation, but central actors in the story of human inquiry. By embracing the challenge, humanity stands poised to uncover new layers of cosmic knowledge, to marvel at the universe's mysteries, and to expand both scientific and philosophical horizons in tandem.